Imagine running a cosmic census and realizing the numbers refuse to add up. You count the stars, the glowing gas, the dust lanes, the planets, every bright thing telescopes can register, and then gravity taps the ledger and says, "You are missing most of the mass." Whatever this missing component is, it does not shine, it does not meaningfully block light, and it barely seems to interact with the rest of physics. Yet its gravitational pull shapes galaxies, binds galaxy clusters, and helped sculpt the largest structures in the universe. We call it dark matter, and the attempt to identify it has become one of the most stubborn detective stories in modern science. Decades of clever ideas, underground detectors, space telescopes, and particle accelerators have chased a suspect that never leaves fingerprints, only an unmistakable tug on everything around it. In this video, we will lay out what dark matter must be able to do, what observations force it to exist, and the leading candidates for what it could be, from heavy invisible particles to ultralight quantum fields, from shadowy neutrinos to primordial black holes, along with the reasons each proposal keeps slipping through our hands. To see how this mystery began, rewind to a simple measurement that turned into a crisis. In the 1930s, Swiss-American astronomer Fritz Zwicky studied the Coma cluster, a crowded metropolis of galaxies bound together by gravity. He measured how fast those galaxies were moving around the cluster and found speeds so high that the cluster should have flown apart if its gravity came only from the matter we can see. The luminous galaxies and hot gas simply did not provide enough mass to keep the system intact. Zwicky concluded that an unseen component had to be supplying most of the gravitational glue, and he gave it a name in his native language, Dunkle Materie, meaning dark matter. Many researchers at the time treated it as an odd claim, partly because the data were limited and partly because Zwicky had a sharp, confrontational reputation. But the discrepancy he pointed at had a way of surviving skepticism, and it lingered in the background, waiting for better observations to turn a strange idea into a central problem. Fast forward to the 1970s. Vera Rubin, a pioneering American astronomer, was studying the rotation of galaxies, particularly the speeds of stars in the outer regions of spiral galaxies. Think of a spiral galaxy like our Milky Way. Most of the stars and glowing gas are concentrated in the center and in the spiral arms. Far out from the center, there's not much visible. If you applied our understanding of gravity, using principles similar to how planets orbit the sun, you'd expect stars farther from the galactic center to orbit slower than those closer in. This is just like in our solar system. The outer planets move more slowly around the sun than the inner planets because the sun's gravity gets weaker with distance, and most of the mass, the sun, is at the center. So, by analogy, a galaxy should have most of its mass in the bright center, and stars at the outskirts should be moving more leisurely. But Rubin and her collaborator Kent Ford found the opposite. The stars in the outskirts were orbiting just as fast, sometimes even faster, than those closer in. In other words, the galaxy's rotation curve, a plot of orbital speed versus distance from center, was flat or rising, not falling off as expected. This was a stunning result. It implied that the visible material, stars, gas, dust, was not the whole story. There had to be extra unseen mass extending well beyond the visible edge of the galaxy, creating additional gravity to speed up those outer stars. In galaxy after galaxy they studied, the same pattern appeared. It was as if each galaxy was sitting in a gigantic, hidden halo of matter that we couldn't see. This was strong evidence that something dark and massive surrounds galaxies. It didn't stop there. Over the years, multiple lines of observational evidence all converged on the same conclusion. There's a lot more mass out there than meets the eye. For example, in clusters of galaxies, like the ones Zwicky studied, scientists can measure the mass in 3 independent ways. 1, by the motions of the galaxies, like Zwicky did. 2, by the X-ray glow of the hot gas in the cluster. Hotter gas needs more gravity to hold it in, so its temperature tells us the gravitational pull. And 3, by a phenomenon called gravitational lensing, the bending of light from background galaxies due to the cluster's gravity. All 3 methods agree that clusters contain far more mass than the visible matter alone can provide. Typically, the measurements show that about 5 to 6 times more mass is present than what we can account for with normal matter. This ratio, roughly 5 parts dark matter to 1 part normal matter, keeps popping up. One particularly dramatic piece of evidence comes from something called the bullet cluster. This is actually 2 galaxy clusters that collided with each other in a kind of cosmic car crash. When clusters collide, the individual galaxies, which are relatively small compared to the space between them, mostly pass by each other without colliding. Galaxies are like grains of sand in 2 colliding sand clouds, mostly missing each other. But the clusters also contain a lot of hot gas. This gas actually makes up most of the normal, visible matter in clusters, far more mass than the stars of the galaxies themselves. When the clusters smashed through each other, their hot gas clouds did collide and got stuck in the middle, slowing down and heating up, like 2 clouds of smoke hitting each other and coalescing. Now, here's the amazing part. Astronomers mapped where most of the mass was in this collision by using gravitational lensing. They observed how the bullet cluster bent background light. They found that the bulk of the mass was not where the hot gas ended up. Instead, the mass had passed right through, carried by something that didn't collide at all, presumably the dark matter halos of the original clusters. In effect, the dark matter in each cluster just sailed through the collision, because dark matter particles don't interact, or at least very weakly interact, with anything except via gravity. The visible gas, however, got stuck in the center. So after the collision, you see the hot gas pooled in the middle. We can detect that via X-ray telescopes. But the centers of mass, traced by lensing, are offset from the gas around the locations of the now separated cluster galaxies. This observation is considered a smoking gun piece of evidence. It's very hard to explain with any theory that doesn't involve some kind of invisible matter. If the gravity in clusters were just due to normal matter and some modified gravity law, you wouldn't expect to see the gravity displaced from the normal matter like that. But with dark matter, it makes perfect sense. The collision separated the non-interacting dark matter from the colliding normal matter. The bullet cluster basically shows us a picture of dark matter and normal matter parting ways during a cosmic impact. Beyond galaxies and clusters, there is evidence for dark matter imprinted in the universe's earliest light, the cosmic microwave background, or CMB. This faint glow from the Big Bang preserves a delicate pattern of tiny temperature variations across the whole sky, like a snapshot of the universe when it was still young. By measuring those subtle ripples, scientists can infer how much ordinary matter existed, how much unseen matter must have been present, and how gravity was already shaping everything. The conclusion is hard to escape. The observed pattern is only consistent with a universe where invisible matter outweighs normal matter by a wide margin, and where this hidden component began steering cosmic evolution very early, only about 380,000 years after the Big Bang. If dark matter were absent, that ancient light would look noticeably different. and the later growth of galaxies in the cosmic web would fail to line up with what telescopes map today. So by now, abundant evidence from many independent sources, galactic rotation, cluster dynamics, gravitational lensing, the cosmic microwave background, the distribution of galaxies on large scales, and more, all point to the same conclusion. There is a lot of invisible mass out there. We call it dark matter. In fact, by current estimates, roughly 27% of the universe's total energy content is dark matter. For context, normal matter, everything that makes up stars, planets, gas, dust, us, is only about 5%. The rest is an even weirder component called dark energy. Another way to put it, about 85% of all the matter in the universe is dark matter, and only 15% is the ordinary stuff. If you imagine all the galaxies, stars, nebulas, and so on as the tip of an iceberg, dark matter is the enormous bulk of ice submerged below the water, unseen but vastly more massive. All right, so evidence for dark matter is overwhelming. It's one of those rare cases in science where we are sure something exists, yet we have almost no idea what it actually is. Normally, in physics, you detect a phenomenon first directly, like you see a new particle in a detector, or observe a new type of star through a telescope, and then you study its properties. Here, it's the opposite. We infer dark matter's existence from its gravitational effects, but we haven't caught dark matter itself directly. It's both frustrating and fascinating, a cosmic mystery of the highest order. So, what do we know about dark matter so far? We know it exerts gravity, which is how we detect it. We know it doesn't emit light, otherwise we'd have seen it by now. Even if it were just dim, telescopes would catch the glow. But it's truly invisible in all parts of the electromagnetic spectrum. Visible light, radio waves, X-rays, everything. We also know it doesn't absorb light in any appreciable amount. For example, clouds of dust in space absorb light and can be seen as dark patches. Dark matter isn't like that either. It's transparent. Essentially, it does not interact with electromagnetic forces, hence the dark, really meaning transparent quality. We also have some clues about how it behaves. Dark matter seems to form halos around galaxies. It's more spread out than the visible matter. In a galaxy, the stars are mostly in a disk, for spirals, or a more concentrated ellipsoid, for ellipticals. But the dark matter forms a big spherical halo enveloping the galaxy and extending well beyond the visible edges. It's like an invisible sphere of mass, the center of which coincides with the galaxy's center, but reaching out much farther. In clusters of galaxies, dark matter is distributed roughly along with the cluster, but as we saw with the bullet cluster, it doesn't stick or collide. Dark matter. Halos can pass through each other largely unaffected. Another thing we know, dark matter had to be around early in the universe to help form galaxies. Computer simulations of the universe's evolution show that if you only include normal matter, you can't form galaxies and clusters as quickly as we did in the real universe. The normal matter, gas, would take too long to clump together because radiation pressure and other effects keep it from collapsing fast. But if you sprinkle in dark matter, especially a type called cold dark matter, which means the dark matter particles move slowly compared to the speed of light and clump easily, the dark matter gravitates into clumps and filaments first, providing gravitational wells into which normal gas can fall and form stars and galaxies. It's like dark matter is the invisible scaffolding or skeleton on which visible structures grow. Simulations with cold, dark matter produce a universe that looks like ours, a cosmic web of filaments and clusters, with galaxies forming along the densest spots. very similar to what large telescopes observe at the biggest scales. So whatever dark matter is, it must behave like this cold component that seeded structure formation. We also have ruled out a lot of possibilities. For instance, could dark matter just be normal matter that's not lit up, like cold gas, rocks, blackened stars, or planets? If it were normal baryonic matter, the stuff made of protons, neutrons, electrons, we'd have some issues. First, in the early universe, the abundance of light elements like helium, deuterium, lithium, produced during the first few minutes after the Big Bang, what we call Big Bang nucleosynthesis, is very sensitive to the total amount of normal matter. Those calculations match the amount of normal matter we infer from CMB and other measures, that approximately 5%. If there were a lot more normal matter hidden somewhere, the early universe would have made different amounts of those elements, and our observations would disagree. But they don't. So most dark matter cannot be normal atomic matter. What about black holes, dead stars, or planets? Those are ordinary matter too, just faint or non-shining. For a while, astronomers wondered whether the Milky Way's halo might be packed with massive compact objects such as black holes, neutron stars, old white dwarfs, or even rogue planets, grouped under the nickname MACOs, short for massive astrophysical compact halo objects. If that were true, these bodies would sometimes drift in front of distant stars and briefly magnify their light through gravitational microlensing, creating a distinctive, time-shaped brightening. Surveys monitored huge numbers of stars in the Magellanic Clouds and toured the galactic bulge looking for that signature, and they found far too few events. The takeaway was blunt. Objects in the relevant mass range, from roughly a fraction of the sun's mass up to several suns, exist, but not in the quantities needed. So a halo made mostly of hidden stars, planets, or stellar remnants cannot explain dark matter. Black holes deserve a special mention. Normal stellar black holes, the ones formed from stars, also can't be numerous enough to be all the dark matter. The microlensing results and other constraints cover them. But what if the universe made black holes in other ways? This gave rise to the idea of primordial black holes. Black holes formed in the extreme conditions shortly after the Big Bang, rather than from collapsing stars. If certain regions of the infant universe were denser than average, they could collapse under their own gravity into black holes, perhaps ranging in size from tiny microscopic ones up to huge ones. If enough primordial black holes formed, they could act as dark matter. This idea has been periodically popular, especially when other particle searches come up empty. Primordial black holes have the appeal that we know black holes do exist and are allowed in physics, unlike entirely new particles which we haven't seen yet. However, primordial black holes as dark matter have also faced many constraints. Hawking's theory of black hole evaporation, Hawking radiation, tells us tiny black holes would evaporate over time, potentially leaving signatures like bursts of gamma rays. We haven't seen those, which rules out some small mass ranges. Slightly larger ones, still far smaller than a star, would have other astrophysical effects, like potentially disrupting stars or white dwarfs if they pass through, and we don't see those effects either. Medium mass black holes, say between the mass of the Moon and the Sun, are heavily constrained by the same micro-lensing searches. We just don't see enough lensing events for those. What about bigger ones, like tens of times the Sun's mass? Interesting story. When the LIGO Gravitational Wave Observatory started detecting black hole mergers, two black holes spiraling together and merging, many of the black holes detected were in the range of 20 to 30 solar masses, which was a bit unexpected. Those are somewhat heavier than many known stellar remnant black holes. This led some to speculate, hey, maybe these are primordial black holes, and maybe dark matter is black holes of around 30 solar masses. There were even papers trying to see if the statistics of LIGO detections could imply a population of such black holes floating around. However, further analysis and more data suggested that while you can't rule out some primordial black holes existing, they probably can't make up more than at most a small fraction of dark matter without contradicting other observations. For example, aside from microlensing, the cosmic microwave background puts limits. Too many massive black holes would affect how galaxies form and could disrupt the CMB's smoothness by gravitational effects. As of now, primordial black holes could perhaps compose a slice of the dark matter pie in some mass ranges, but it's very unlikely that all dark matter is black holes. Most researchers have shifted focus to other ideas, though a few keep investigating exotic scenarios with black holes. Okay, so if dark matter isn't just normal matter hiding in dark objects, that means it likely is something fundamentally different, something outside the standard roster of stuff we know. The strong consensus is that dark matter is probably a new kind of particle or family of particles that we haven't discovered yet. This is where the search gets really interesting and maybe a bit absurd in the sense of the extreme lengths we go to try to detect these potential particles. Physicists have proposed a whole zoo of hypothetical particles or entities to potentially explain dark matter. Let's explore the main candidates. Basically, all the things dark matter could be, at least in theory. For decades, one leading idea was the WIMP, short for weakly interacting massive particle. The label is almost a job description. A hefty, electrically neutral particle that slips past ordinary atoms because it does not couple to light and only very rarely interacts through the forces we already know. It became popular because of an eerie coincidence in the early universe. In the first hot moments after the Big Bang, this kind of particle would have been produced in huge numbers and repeatedly eliminated when two of them met, converting their mass into lighter particles. As the universe expanded and cooled, those encounters would have become less frequent until the population stopped efficiently annihilating, leaving a stable leftover that simply drifted through the cosmos. For a broad range of plausible masses and interaction strengths, the amount that survives ends up close to the dark matter abundance inferred from cosmology, which made the idea feel uncannily natural. That is why the WIMP stayed at the center of the hunt for so long, even as experiments have been forced to chase ever fainter signals. Furthermore, particle physics theory offered some candidates that fit the WIMP profile. The most celebrated one comes from supersymmetry. Supersymmetry, often shortened to SUSY, is a theoretical framework that extends our standard model of particle physics. In simple terms, it predicts that every known fundamental particle has a heavier partner particle. For example, the electron, a particle of matter, would have a partner called a selectron. Quarks would have squarks. The photon, force particle of electromagnetism, would have a partner called a photino, and so on. Many of these partner particles would be unstable and decay quickly. But an important detail is that in many versions of supersymmetry, there is a lightest supersymmetric particle, often a neutralino, which is a mix of the supersymmetric partners of the photon, Z boson, and Higgs boson. If the theory is correct, this lightest superpartner can't decay into anything else because it's the lightest one that carries a new conserved quantum number, so it would be stable. And typically, the neutralino would be neutral, no electric charge, fairly massive, perhaps tens to hundreds of times a proton's mass, and interacting only through the weak nuclear force, And gravity, of course. That's basically a WIMP. So for a long time, many physicists thought the neutralino from supersymmetry was the prime dark matter candidate. It was a beautiful fit. Supersymmetry helps solve other theoretical issues in physics, like why the Higgs boson's mass is what it is, and as a bonus, it provided a natural dark matter particle. Supersymmetry also gives other possible dark matter candidates, for instance, the gravitino, the partner of the graviton, the hypothetical quantum of gravity, or the axino, partner of the axion, which we'll talk about soon. But those depend on details of the model. The neutralino was the star of the show for WIMPs. However, the WIMP, especially the SUSY-WIMP paradigm, has hit a big snag. We haven't found any evidence of it yet, despite very intense efforts. The Large Hadron Collider, LHC, the world's most powerful particle accelerator, started running in 2010, with one of its goals being to either discover supersymmetric particles or find the WIMP directly. So far, the LHC has not seen any clear sign of supersymmetry. We found the Higgs boson, great triumph, but nothing beyond the standard model has popped out. That doesn't mean supersymmetry or WIMPs aren't there. It could mean that if they exist, they're just a bit heavier or interact a bit more weakly than our initial optimist expectations. But it does mean there's no easy, obvious discovery of those particles at the LHC's current reach. Additionally, a number of dedicated dark matter detectors around the world have been specifically looking for WIMPs for years, and those have also come up empty. We'll delve more into the detector story in a bit. The lack of any signal, despite ever-improving sensitivity, has started to make some scientists wonder if the WIMP idea is just wrong, or if we've been unlucky, or maybe WIMPs are there, but with properties that elude current detection methods. It's worth noting that ideas in the same spirit keep evolving. Even if the simplest supersymmetric version is under pressure, other models can still produce a stable, heavy, electrically neutral particle. In little Higgs theories with T-parity, for example, a new symmetry can protect the lightest new particle from decaying. In extra-dimensional scenarios, the lightest Kaluza-Klein excitation can also be stable and act as dark matter. The details differ, but the theme is consistent. Many extensions of the standard model naturally leave behind a long-lived massive particle that moves slowly enough to clump and build cosmic structure. In that sense, the WIMP picture remains a useful target even as the preferred models keep shifting. Now, let's switch gears from heavy to light. One major class of candidates is the axion, a particle that was originally introduced to solve a specific theoretical puzzle, and later turned out to fit remarkably well into the dark matter story. In the late 1970s, physicists were grappling with an oddity in quantum chromodynamics, QCD, the theory of the strong nuclear force. QCD seemed to allow effects that should give the neutron a measurable electric dipole moment, meaning a slight asymmetry in its charge distribution. Experiments, however, found no such dipole moment, or at most, an extremely tiny one. To resolve this strong CP problem, Roberto Piche and Helen Quinn proposed a new symmetry, which in turn implied a new particle. Frank Wilczek helped develop the idea and jokingly suggested naming it after a laundry detergent because it was meant to clean up the theory. If it exists, the axion would be extraordinarily light, potentially in the microelectron volt mass range, which is millions of times lighter than an electron. Even more importantly, it would couple to ordinary matter only very weakly. A helpful way to think about this is that it behaves like a nearly invisible background, with one especially useful feature for experiments. In a strong magnetic field, it can sometimes convert into a photon, and the reverse conversion can also occur. As a dark matter candidate, it does not rely on the standard thermal freeze-out mechanism often discussed for WIMPs. Instead, early universe dynamics tied to Pecky-Quinn symmetry breaking can generate a large relic abundance through non-thermal production. You can picture a field that gets set into a particular configuration as the universe cools, then begins to oscillate, with those oscillations corresponding to the particle population. If the axion is stable, that relic population can survive to the present day and potentially account for the observed dark matter density. In ultralight versions of this idea, the wave nature becomes important on galactic scales. The quantum wavelength can reach kiloparsec distances, so structure formation is influenced by interference and wave effects rather than purely by particle clustering. Simulations of fuzzy dark matter often show smoother, more extended cores in small galaxies and less structure on the tiniest scales, which could ease some tensions that arise in the simplest cold dark matter picture. Detection is challenging because this candidate does not produce the classic nuclear recoil signatures expected from many WIMP searches. The most developed strategy instead leverages photon conversion. Experiments place a strong magnetic field inside a resonant microwave cavity, tune the cavity to a frequency set by the particle mass, and listen for an extremely faint excess signal. By scanning frequencies step by step, setups like ADMX effectively search for a narrow tone hidden in noise, much like trying to tune an old radio to a very weak station. So far, there is no confirmed detection, but the excluded range of possible properties has steadily grown, and complementary approaches using lasers and precision spin-based techniques continue to expand the search. Related to axions is a broader class of hypothetical low-mass particles often called axion-like particles, ALPS, or even a hidden sector of particles. Some theories suggest there might be an entire hidden sector of particles that includes not just a dark matter particle, but also forces that act only on dark matter. For instance, there could be a force analogous to electromagnetism in the dark sector, mediated by a particle often termed a dark photon. The dark photon would be like a cousin of the photon, but it doesn't interact with normal electric charge, only with a possible dark charge that dark matter particles carry. If the dark photon is lightweight, it could cause dark matter particles to scatter off each other. This is called self-interacting dark matter. Why bother with that? Because it might help with certain observations. Self-interacting dark matter can make the distribution of dark matter in small galaxies less tightly peaked and more spread out, since the particles scatter and thermalize a bit, potentially solving the cusp core problem, where pure cold dark matter predicts a sharp density spike at centers of dwarf galaxies, but observed dwarfs have more cored, flat profiles. Also, if dark matter scatters with itself, it might form dense droplets or affect how it behaves in collisions like the bullet cluster. Though too much self-interaction is also bad because bullet cluster shows dark matter largely passed through. It's a balancing act. But the idea of a dark photon and dark forces basically says, maybe dark matter isn't just a single particle, but part of a hidden world with its own interactions, an entire dark sector of which we see only gravity effects leaking over. This concept is appealing to some theoretical physicists because it's not uncommon in physics to have multiple sectors, the visible sector and a hidden sector, that have limited coupling. If a dark photon has a tiny bit of mixing with the regular photon, we might detect it in certain experiments, like tiny forces or slight deviations in how electromagnetism behaves at certain scales. People are looking. Next up, neutrinos. We already have neutrinos in the standard model. In fact, neutrinos are kind of like a form of dark matter in the sense that they are neutral, very tiny in mass, and don't interact much. They only feel the weak force and gravity. If neutrinos had been heavier, they could have been a dark matter candidate. But here's the catch. Neutrinos, the ones we know, 3 flavors from Standard Model, have been measured to have extremely low masses, much less than an electron's mass. And, importantly, they move very fast, nearly the speed of light, especially in the early universe. Neutrinos would be what we call hot dark matter, and hot dark matter just doesn't fit the observed universe's structure. If dark matter were all fast-moving like neutrinos, structure, galaxies, clusters, would form differently. Small structures would have a hard time forming because fast particles stream out of small clumps. Imagine trying to hold a bunch of bugs in a shallow bowl versus molasses. Neutrinos are like energetic bugs that just escape clumps. Observations show we need more of a cold component. In fact, constraints from cosmology tell us that normal neutrinos contribute at most a few % of the dark matter. Because neutrinos exist and have some mass, they do count toward a bit of the total mass energy budget, but not much. However, this leads to sterile neutrinos. A sterile neutrino is a hypothetical type of neutrino that doesn't even interact via the weak force, whereas normal neutrinos do via the weak nuclear force. It's sterile to all forces except gravity. Sterile neutrinos could have a wider range of masses. If one existed with a mass of a few kilo-electron-volts, it would be heavier than normal neutrinos, but lighter than WIMPs. We'd call that warm dark matter, intermediate between hot and cold. Warm dark matter like that would smooth out some small-scale structure, potentially solving the too many dwarf galaxies problem that pure cold dark matter seems to have, but not to the extent of hot dark matter. A Covey sterile neutrino is an interesting candidate. How would we know it's there? Sterile neutrinos could potentially decay very slowly, since they're not truly stable if there's a tiny mixing with normal neutrinos. A sterile neutrino might decay into a lighter neutrino and a photon. That photon would carry energy roughly half of the sterile neutrino's mass. So if you have, say, a 7 kilo-electron-volt sterile neutrino, it could produce a 3.5 kilo-electron-volt X-ray photon when it decays. Astrophysicists have indeed looked for mysterious X-ray lines in space. In 2014, a group reported finding an unexplained X-ray emission line at around 3.5 kilo-electron-volts coming from galaxy clusters and other places. They speculated it could be sterile neutrinos decaying. This caused a big stir. However, follow-up studies have been mixed. Some see hints of it, others don't, and some suspect it might be an artifact of the instruments or analysis. As of now, there's no consensus that we have a real dark matter decay line. If it's there, it's subtle. But the fact that serious astronomers are combing through X-ray telescope data for lines that shouldn't be there shows how creative the dark matter search has become. Sterile neutrinos with other masses, like in the electron-volt range or heavy ones in the giga-electron-volt range, have also been considered, and there are experiments and observations trying to cover those possibilities, often via their subtle effects on oscillations of normal neutrinos or structure formation patterns. We're not done with the roster of candidates. Let's talk about some exotic macro objects. Basically, things that are not fundamental particles, but weird conglomerates that could be dark matter. One idea is something called quark nuggets or strangelets or nuclearites. These are hypothetical clumps of quark matter. You might know that normal matter is made of atoms, which have nuclei, made of protons and neutrons, which themselves are made of quarks. In ordinary matter, quarks come in 2 flavors primarily: up and down quarks with a sprinkling of electrons around to make atoms. But there's also a heavier quark called the strange quark. There's a long-standing idea that maybe there is a stable combination of quarks that includes strange quarks. Basically, a little chunk of matter that is like one giant nucleus made of up, down, and strange quarks in roughly equal measure. This is sometimes called strange quark matter or a strangelet, and it might be more stable than atomic nuclei if it reaches a certain size. If during the early universe some of the quark gluon plasma coalesced into these stable nuggets of strange matter, they could be flying around today as dark matter. They'd be small, maybe asteroid mass, but centimeter size, or many could be smaller mass, and they'd be virtually invisible. They don't interact with light much, being neutral overall and dense. There have been experiments and searches for signs of these too. For example, detecting seismic signals if one went through Earth, or looking for tiny damages in materials left by such a nugget passing through. So far, nothing conclusive. Quark nuggets remain a speculative idea at the fringe, but an interesting one. Another concept, Bose-Einstein condensates or solitons of new fields. I touched on this with fuzzy dark matter, but more generally, if dark matter is some field, like a scalar field, it could form macroscopic quantum structures. Some researchers have proposed that dark matter could be a field that forms stable clumps called Q-balls or other soliton-like configurations. These would be like particles the size of, say, a soccer ball or a small asteroid, but made of a field's collective excitation. This is really out there theoretical physics stuff, and there's no evidence such things exist. But mathematically, some particle theories allow for composite objects that act like a single massive particle, a bit like how a nucleon is made of quarks but acts as one particle, or how a Cooper pair in a superconductor acts as one unit. If dark matter were something like that, detecting it would be even trickier, but maybe they could cause occasional weird interactions or events. Again, nothing seen yet, but the fact these have been proposed underscores that when the obvious candidates don't show up, scientists widen the net a lot. We also have the notion of extra-dimensional candidates. I mentioned Kaluza-Klein particles. Let's explain that a bit. If space has more dimensions than the three we directly sense, some particles might have momentum or waves that extend into those extra dimensions. From our 3D perspective, that momentum shows up as extra mass, sort of like how a guitar string's harmonics have higher energy. That means, for example, the photon might have a heavier first harmonic version of itself in a space with an extra dimension. That would look to us like a new heavy particle that's stable due to some symmetry. Often, a parity symmetry in these models ensures the lightest Kaluza-Klein mode can't decay to ordinary particles. That lightest mode could be a dark matter particle. Similarly, in some theories, the graviton, the hypothetical quantum of gravity, could have extra-dimensional versions that are heavy and maybe one is stable. These ideas tie into some advanced physics, including string theory and brane world scenarios. While they sound fantastical, they're on the table as possibilities. They basically still fall under some kind of WIMP in terms of how we'd search for them. They'd be heavy and fairly slow-moving, but their origin is in geometry of space itself. Another interesting idea is asymmetric dark matter. This concept is inspired by a big fact. The universe has more matter than antimatter. In fact, as far as we can tell, all the antimatter that once existed, in equal quantity to matter just after the Big Bang, got annihilated, leaving a tiny excess of matter, us. That tiny excess, on the order of 1 part in a billion of the original matter, is what remained to form all normal atoms. This is called baryon asymmetry of the universe. Now, no one fully understands how that asymmetry came to be. That's another big mystery in cosmology and particle physics. But clearly something happened to create an imbalance between matter and antimatter in the early universe. Asymmetric dark matter theories propose, what if dark matter is also the result of an asymmetry in a dark sector? Maybe originally there were equal amounts of dark matter and anti-dark matter that annihilated each other, but a tiny excess of dark matter particles remained, similar to the baryon excess. If that's the case, there might be some relation between the amount of normal matter and dark matter in the universe, even possibly linking their densities or masses. For example, if dark matter particles were about 5 times heavier than protons, and if the processes that created the asymmetry yielded similar number imbalances, you'd naturally get 5 times more mass in dark matter than normal matter, which is what we see. This might not be just a coincidence. It could hint at a common origin. Some models indeed tie the genesis of baryons and dark matter together, like interactions that convert between baryon number and dark matter number in the early universe. In such models, dark matter wouldn't annihilate away completely because there's an excess of one over the other, meaning today there might be no anti-dark matter left to annihilate with, which implies that unlike a WIMP scenario, you wouldn't expect to see dark matter annihilating in space today, because it mostly annihilated long ago, and the rest is just stable leftovers, like protons are stable leftovers of baryogenesis. Asymmetric dark matter is harder to test with something like gamma-ray searches, since no annihilation signals expected, but one might hope to produce it at colliders or see it scatter in detectors. It also often implies the dark matter particle could be lighter, maybe a few GeV, around the proton mass scale or a bit more. Those lighter dark matter particles are actually harder for many detectors to see, which might explain why we haven't seen anything if we were looking in the wrong mass range. Whew. As you can see, the list of candidates is long. It ranges from massive black holes to ultralight ghostly particles, from things in familiar physics like neutrinos to entirely new concepts like supersymmetric partners or extra-dimensional modes. It's as if dark matter is a puzzle with 1,000 pieces, and we're not sure which pieces fit. We just know the end picture should account for that 85% missing mass. Now, with all these ideas on the table, you might be thinking, surely, in all that, we must have found something by now, some hint of one of these candidates? This is where the story gets a bit frustrating and why we call it an absurd search. Because despite decades of trying, we have not confirmed a single direct detection of dark matter yet. It's not for lack of trying. The effort has been Herculean. Let's talk about what scientists have been doing to try to catch dark matter in the act, and why it's so hard. One major approach is direct detection. Imagine dark matter is made of particles, WIMPs, axions, etc., that are floating around us right now. Yes, right now as you listen to this. If dark matter is a particle, billions of them are likely passing through you every second without a trace. Our solar system is moving through the galaxy's dark matter halo, and at our location, it's estimated there could be around 1 trillion dark matter particles in every cubic meter, if they have typical WIMP masses, say. They move fast, maybe a few hundred kilometers per second. That's the orbital speed of our sun around the galaxy. Normally, we'd never notice them, because they hardly interact. But what if, very occasionally, one of those particles does bump into something? In particular, bump into an atom in a detector? This is what direct detection experiments look for: a dark matter particle scattering off the nucleus of an atom, or sometimes off an electron, but usually nucleus in a detector, causing the atom to recoil and produce a tiny, measurable signal. However, these signals are expected to be extremely small and rare, because if dark matter particles interacted strongly, we'd have seen them already. So they must interact super weakly, maybe only one collision per ton of detector per year, or something like that, depending on unknowns. So to catch these faint interactions, you need two things: a very sensitive detector and a very quiet environment to avoid false signals from other sources, which we call background. Scientists have gone deep underground to shield from cosmic rays and built huge detectors made of ultra-pure materials. One popular method uses liquid noble gases like liquid xenon. Xenon is great because you can get it very pure, and it scintillates, gives off a faint flash of light, and also lets you detect ionization when a particle hits it. The current frontrunner experiments like Xenon NT in Italy, Lux Zeppelin in the USA, and Panda X in China all use large vats of liquid xenon, weighing several tons. They are surrounded by photodetectors to catch any tiny flash of light and electric fields to gather ionization electrons. If a dark matter particle smacks a xenon nucleus, the nucleus will recoil a bit, like a tiny billiard ball collision, and that recoil causes the xenon atom to excite and ionize some neighbors, leading to a flash and some freed electrons. Those signals can be detected. From the ratio of the light to charge signals, scientists can distinguish whether the hit was likely a nuclear recoil, which is what WIMPs would cause, or an electron recoil, usually caused by stray gamma rays, or beta decays, which are background. They also use the 3D position info of the event, via timing of signals, to know if it happened in the middle of the tank. Good, likely dark matter, or at least something that penetrated deep. Or at the edges, likely some background radiation from the walls. It's an incredibly sophisticated setup. What have these experiments seen? Nothing definitive. They've been running for years. Occasionally, one will see a slight excess of events that gets people excited, but then either further data or other experiments refute it. For instance, an older detector called DAMA/LIBRA in Italy claimed a detection, not of individual events, but of a pattern. They observed that the event rate in their detector changed over the year in a sinusoidal way. This is interesting because as Earth orbits the Sun and the Sun moves through the galaxy, the relative speed of the Earth through the dark matter halo should modulate annually. We go a bit faster in June, a bit slower in December relative to the dark matter wind. This could cause a slight increase then decrease in the interaction rate, an annual modulation signal, which is considered a telltale signature of dark matter if seen. DAMA claims to see exactly that, year after year, a consistent annual cycle. That sounds like game over, we found it, right? The catch: no other experiment in the world sees any hint of dark matter, and the DAMA signal, if it were dark matter, is actually in conflict with what others that are more sensitive would have seen. This has led to a lot of controversy. The prevailing view is that DAMA's detection might be due to some experimental artifact or an unknown background that also modulates with seasons, perhaps something environmental like temperature or cosmic ray muons, though they claim to have accounted for those. It's unclear, but since multiple other detectors like Xenon, LUX, CDMS, etc., have basically ruled out WIMPs in the range that would cause DAMA's signal, most scientists are skeptical of the DAMA claim. There are ongoing efforts to replicate DAMA's setup in the northern and southern hemispheres, to see if they also get a modulation. If one sees a phase flip in the southern hemisphere, it would confirm it's dark matter, since the seasonal phase would invert between hemispheres if it's due to our motion, but not if it's some mundane seasonal effect like temp. This is all to say, it's a tough business. Even when one group claimed a hint, it turned into a 20-year puzzle still not resolved, and likely not the dark matter we seek. Other experiments like CDMS, using cryogenic crystals to detect phonons from collisions, and CRESST, using scintillating crystals, have also looked, as have others, using liquid argon, like DEAP or dark side experiments. The cumulative result, WIMPs, if they exist with the expected interactions, must interact even more weakly than we thought because we haven't seen them. The sensitivities are now so high that these detectors could have seen interactions way rarer than even neutrinos cause. Yes, neutrinos, those pesky, barely interacting particles, are actually becoming a background for the next-gen dark matter detectors because occasionally a solar neutrino can hit a nucleus and mimic a dark matter event. We're approaching what's called the neutrino floor, where detectors become so sensitive that irreducible neutrino interactions will fog the data, making it very hard to push further. Yet, the experiments are still going, with new ones planned. For example, a next generation like Darwin in Europe aims to use an even bigger xenon target to push sensitivity further, maybe to see certain types of dark matter, or in case interactions are just at the threshold of current experiments. How about indirect detection? That's the approach of looking for products of dark matter annihilations or decays in space. If dark matter particles can annihilate each other, then in regions of high dark matter density, like the centers of galaxies or dwarf satellite galaxies where there's a high concentration of dark matter and not much other activity, we might see excess high-energy radiation. Many searches have targeted gamma rays in particular, since a dark matter annihilation could produce gamma ray photons either directly or through cascades. The Fermi Gamma Ray Space Telescope spent years mapping the gamma ray sky. There was indeed the observation of a kind of spherical glow of gamma rays at the center of our Milky Way, the so-called galactic center GV excess, which some argued could be consistent with dark matter of mass around 30 to 50 GeV, annihilating into quarks or something at a slow rate. But it's hard to know for sure. There are lots of gamma ray sources in the galaxy. More detailed studies and new data pointed out that the spatial distribution of that excess might correlate with the stellar distribution, which would imply it's likely from many unresolved millisecond pulsars or some other astrophysical sources, not dark matter. It's still debated, but no consensus that it's dark matter. Other indirect searches look at cosmic rays. For instance, the AMS-02 detector on the International Space Station reported an unexpected excess of positrons, anti-electrons, in the cosmic rays at certain energies. One way to get extra positrons is if dark matter particles annihilate and produce those. Again, excitement ensued. Maybe this is dark matter. But astrophysical explanations exist too, notably pulsars, rapidly spinning magnetized neutron stars, could be spewing out positrons. At the moment, it looks more likely the positron excess is astrophysical. It didn't match perfectly some simple dark matter models either, like it was a bit too narrow in energy range to easily be dark matter, but who knows? Neutrino telescopes like IceCube have searched for neutrinos coming from the center of the Sun or Earth, which could indicate WIMPs that got gravitationally captured and then annihilated in the Sun's core, producing neutrinos. Nothing significant found there either. And the LHC, as I mentioned, has looked for missing energy events. Those would be events where something like a quark and a hypothetical WIMP are produced together. You'd see the quark as a jet of particles, but the WIMP leaves the detector invisibly, so you get an imbalance of momentum, like a kick with no counter-kick. They've seen events with imbalanced momentum, but none that stand out above expected backgrounds from neutrinos or other standard model processes. They also specifically looked for signs of supersymmetric particle decays that would end in stable neutralinos, but nothing has emerged. So here we are. All these laborious searches have turned up no confirmed dark matter particle. It's as if we're playing a game of hide and seek with the universe's missing mass, and dark matter is the ultimate hide and seek champion, hiding not just in one tricky spot, but in a way that we can't even tell what we're looking for exactly. Now, this doesn't mean the search is hopeless or was foolish. In fact, these experiments have achieved amazing feats. They have helped develop new technologies, ultra-pure materials, cryogenics, novel sensors. They also have constrained models, which is valuable. By not finding something, we learn what it isn't. We've ruled out a huge swath of possible WIMP properties, for example, which tells theorists to adjust their models or think of new ones. However, it has forced physicists to reckon with the possibility that maybe our initial guesses were off. That's why alternate ideas like axions or very light dark matter or super heavy dark matter have gained more attention. The search is broadening. We even see new types of experiments being devised, like using quantum sensors for ultralight dark matter, which might cause tiny oscillations in atomic energy levels or physical constants, or using atomic clocks to see if dark matter passing through might tweak the ticking rate ever so slightly, or using resonant bar detectors, like old gravitational wave detectors, to catch vibrations from a passing wind of dark matter that might interact with phonons. There are also ideas of looking for signals in astronomical objects. For example, if dark matter is massive and can interact, it might be captured in neutron stars, and then as it accumulates, possibly trigger the star to collapse into a black hole. We don't see neutron stars collapsing willy-nilly, so that sets limits on certain types of dark matter interactions or masses. If it's too heavy or interacts too strongly with neutrons, for instance, we'd notice because neutron stars would disappear more often. It's amazing how creative the methods have become. The search for dark matter permeates many fields: astrophysics, underground lab experiments, collider physics, and now even precision quantum measurements. In the face of this, a few scientists have asked the uncomfortable question: could it be that dark matter doesn't exist at all? That maybe all these effects attributed to dark matter are actually because we misunderstand gravity on large scales? This is the idea of modified gravity. The most well-known example is MOND, modified Newtonian dynamics, proposed by Mordechai Milgram in the 1980s. MOND is not so much a fully fleshed theory as a sort of phenomenological tweak. It suggests that perhaps at extremely low accelerations, the kind you get at the edges of galaxies, gravity doesn't fall off exactly as in Newton's inverse square law, but rather transitions to a different behavior. With the right function, MOND can actually predict galaxy rotation curves quite well, using just the visible matter distribution. That's impressive. It can fit the rotation of galaxies without dark matter by assuming gravity, or inertia, behaves differently at small acceleration. MOND basically says, for very tiny accelerations, like 100 billion times smaller than what we feel on Earth's surface, the effective gravity becomes stronger than expected, which holds those stars in their orbits without invoking dark mass. There's also a relativistic extension of MOND called TVES, tensor vector scalar gravity by Jacob Bekenstein, and other ideas like modified gravity, MOG, or emergent gravity, proposed by Erik Verlinde, all trying to do away with dark matter by changing the laws of gravity. These ideas remain controversial. Why? Because while they can often explain galaxy rotation curves or certain empirical relations like the Tully-Fisher relation, which is an observed tight correlation between a galaxy's rotation speed and its visible mass, something that naturally falls out of MOND, but is just a result of how galaxies form with dark matter, they typically struggle with other observations. For example, the cosmic microwave background and large-scale structure, the distribution of galaxies, are beautifully explained by dark matter plus general relativity. If you remove dark matter and try to tweak gravity, you have a much harder time getting the universe's early and large-scale picture right. Also, things like the bullet cluster's lensing separation are hard to reconcile with just modified gravity. You'd have to contort the theory to allow mass to sort of be in two places, which is what dark matter allowed, with mass distributions separate from normal matter. Modified gravity theories often would predict the lensing to follow the normal matter, which in bullet cluster, it doesn't fully. That said, modified gravity has had successes in matching galaxy-scale observations that are still not obviously solved by standard dark matter simulations. For instance, MOND naturally explains why the outer rotation speed of galaxies relates to the mass, the Tully-Fisher law, in a simple way. In dark matter theory, that relation is a bit more emergent from complex galaxy formation physics, but it ends up being true as well. However, one might argue the regularities of those relations feel suggestive of something deeper. There's also a spooky thing called the radial acceleration relation, basically a very tight correlation between the observed acceleration in galaxy rotation at a given radius and the acceleration expected from the visible matter alone. It's like there's a one-to-one function that, given the visible matter distribution, tells you the total acceleration, including dark matter effects. And that function is exactly what MOND's formula would give. It's almost as if each galaxy's dark matter distribution is perfectly linked to the visible distribution, which is weird if dark matter is independent and just clumps via gravity. You'd think there could be more scatter or difference. This has made some people think maybe dark matter physics somehow correlates strongly with baryons, or maybe gravity just behaves that way naturally. One intriguing possibility is that maybe both dark matter and modified gravity are part of the story. This might sound contrarian. How can it be both? Here's an example. Some theorists like Sabine Hossenfelder have pointed out that what we call modified gravity could actually be a result of dark matter physics in a way. For instance, a theory where a dark matter particle and a new force between dark matter particles, like a dark photon mediating a kind of fluid behavior, can, in a certain limit, mimic a modification to gravity. Essentially, a dark sector physics could yield an effect that makes it look like gravity changed, even though underlying it there are still particles. Conversely, some modified gravity theories can be thought of as adding extra fields, which, if you quantize them, are like particles too. After all, in physics, particles and fields are two sides of the same coin. So maybe the dichotomy is false. The solution might involve something that in one description looks like a field modification, gravity's law changing, and in another looks like a new fluid or particle component. At this point, though, most mainstream researchers still put their bets on dark matter being a particle or something in that realm, rather than a modification of gravity, simply because the cosmological evidence is hard to argue away. The safe bet is that dark matter is real stuff. We just have to find it. So, where does that leave us? We have a huge mystery. 85% of the matter in the universe is unknown. We have lots of hints of its existence and its behavior, but we don't know its identity. We've tried many ways to detect it directly or indirectly, and it remains elusive. It truly is humbling. Nature has basically left us this giant puzzle piece outside the standard model of physics, and solving it could reveal entirely new physics. Think of past big mysteries. People once thought there was an ether that light traveled through. That turned out not to exist. Instead, we got special relativity. People thought peculiarities in Mercury's orbit were due to a hidden planet Vulcan. Turns out it was a bending of space-time, general relativity. In other cases, though, unseen things did exist. Neptune was discovered because astronomers noticed Uranus's orbit was deviating from expectations. They predicted another planet, and bingo, Neptune was found in 1846. Dark matter is a bit of both analogies. Maybe it's like Neptune, a real unseen thing causing effects. Or maybe it's like the ether. Our model is missing something deeper instead. If it's like Neptune, then eventually we will detect the planet, the dark matter particle, and a Nobel Prize will surely follow. If it's like the ether, then perhaps the theory of gravity or something fundamental will have to change, and that would be just as profound a discovery. The absurdity of the search comes from the contrast. On the one hand, dark matter is everywhere. Right now, dark matter particles, if that's what they are flowing through this room, through your body, through Earth. There's a halo of dark matter enveloping our entire galaxy that outweighs all the stars. And yet, we can't touch it. We can't see it. We can't even feel it. It might as well be a ghost. The universe is seemingly full of an invisible substance that acts like a ghostly glue. It's almost a supernatural concept, except it comes from solid scientific inference. So we build ultra-sophisticated traps for these ghosts. Deep underground laboratories, giant particle colliders, satellite observatories, and each time we come up empty-handed, at least so far, it's as if the universe is teasing us. Yes, there's a big secret here, but I won't give it up easily. Despite the frustration, there's a lot of optimism among scientists. Why? Because history shows that when we push the boundaries like this, we tend to either discover something new or revolutionize our understanding. Either outcome is exciting. If we detect dark matter particles, wonderful. We learn what they are, and a whole new branch of physics opens up. Imagine, if it's supersymmetry, that's huge. If it's an axion that reshapes particle physics and might even solve multiple problems at once. If it's something unexpected, that's even more thrilling. If we continue to not detect anything, and it becomes clear we're on a wrong track, that could point to a paradigm shift. Maybe a new theory of gravity or something unanticipated is needed, which again could shake physics to its core. The search has also brought together different disciplines: astrophysicists, particle physicists, cosmologists, all collaborating. It's driven technological innovations, like those super-sensitive light detectors, ultra-low background techniques, etc. In a way, the pursuit of dark matter has already enriched science, even without the final prize in hand. Let's imagine a scenario. Suppose in the next few years, one of the experiments finally strikes gold. Maybe an underground detector suddenly observes a clear signal that cannot be explained by anything else, and it matches between two different experiments. That would be the moment of discovery. We'd finally have direct evidence of dark matter particles. The next steps would be to characterize it, measure its mass, how often it interacts, etc. That would then feed back into astrophysics. We'd rerun cosmological models with the actual particle properties measured to see if everything lines up. It probably would, because it was inferred from there, but you never know. Surprises can happen. It would be like turning on a light in a dark room, illuminating a whole new sector of the particle world. Alternatively, imagine we definitively rule out the simplest dark matter candidates and still see nothing, and perhaps we find inconsistencies in our gravitational theory that accumulate. We might then lean more towards the idea that a new theory of gravity is needed. That would be a revolution, akin to when Einstein replaced Newton's gravity, though presumably not as dramatic as that, since any new theory would still have to reduce to Einstein and Newton in familiar conditions. As of today, in the year 2025, we don't have that eureka moment yet. We have hints, we have theories, we have null results that guide us. The Ellux Zeppelin experiment recently completed a significant run and, true to form, reported no dark matter found, but pushed the exclusion limits even further, meaning if WIMPs exist, they interact even more weakly than the feeblest interactions we previously thought plausible. The axion searches have yet to snag an axion, but they're probing deeper into the plausible range of axion masses and couplings. New experiments like IAXO, International Axion Observatory, are in the works to ramp up axion detection sensitivity. We have upcoming facilities like the James Webb Space Telescope and other observatories that will help pin down how galaxies form and maybe catch anomalies that hint at dark matter's nature indirectly. There are also plans for next-generation colliders that could, for example, produce heavy particles up to higher masses, which might give clues if dark matter lies in that heavier regime. One way or another, science is pressing forward. We often call dark matter mysterious, invisible, maybe even absurd to search for, but keep in mind, the reason we're so captivated by it is that it solves so many cosmic puzzles. It neatly explains so much of what we see, and it fits naturally in the big picture of the universe's history. Whatever it is, it played a crucial role in shaping everything, including the very galaxy we live in. Without dark matter, the Milky Way might never have formed the way it did, and life as we know it might not exist. We owe a lot to this invisible ingredient. Let's conclude by painting a mental picture. Imagine the night sky. You see the stars scattered across, maybe the faint band of the Milky Way. Beautiful, isn't it? Yet for all that beauty, you're literally only seeing a tiny fraction of what's there. The real bulk of our galaxy is an enormous dark halo extending far beyond the visible stars, an ocean of something we have yet to identify. It doesn't shine, it doesn't announce itself, but it's the scaffold on which those stars are hung. It's the silent partner to the glittering cosmos. The search for dark matter might seem absurd at times, like chasing phantoms, but it's a noble quest. It's humanity trying to fill in a major blank in our understanding of the universe. We don't settle for "it's magic" or "we'll ignore it." We keep investigating. And as daunting as the challenge is, there's a sense of adventure and optimism. Remember, we've been here before with other big mysteries, and eventually, with persistence and creativity, we cracked them. One day, perhaps sooner than we think, a breakthrough will come. Maybe an experiment will hear the faint whisper of an axion, or see the faint glimmer of a WIMP collision, or a clever new observation will point the way. The moment we finally identify dark matter, it will be a historic turning point. Until then, scientists will continue to turn over every stone, tune every detector, and refine every theory in this grand hunt. So the next time you gaze up at the stars, take a moment to appreciate that the most common form of matter out there is something fundamentally alien to us. It's humbling and thrilling. Nature still holds secrets on cosmic scales. Dark matter is a reminder that as much as we've learned, we are far from knowing it all. And it's an invitation, a challenge, to future explorers and thinkers to solve one of the greatest cosmic puzzles of our time. In the end, the absurd search for dark matter might turn out to be one of the most profound journeys science has ever embarked upon. It forces us to confront the unknown and push the limits of technology and imagination. When we finally shine a light on this darkness, we'll not only understand our universe better, we'll also have shown just how far human curiosity and ingenuity can go in unraveling the mysteries of nature, and that perhaps is the most exciting part of all.